fourth question here says, if electric field in a region is radially outward with magnitude E is equal to AR, the charge contained in a sphere of radius r centered at the origin is. Now we need to find the charge enclosed within a spherical surface of radius r in this region, and we know that electric field is always radially outward in this region, and the magnitude of electric field at any given point is AR, where r is the distance of that point from the origin. Now we look at a figure here which explains what is mentioned in the question, and we need to find the charge enclosed within this spherical surface here of radius r, and that is our closed Gaussian surface here. So we'll use Gauss theorem here, which says phi e, the electric flux passing through this closed Gaussian surface, will be equal to Q enclosed by epsilon naught. And we need to find the charge enclosed in this problem. So we can say that from this expression, Q enclosed will be equal to phi e, the electric flux passing through that Gaussian surface, multiplied with epsilon naught. So to go any further, we should find the electric flux passing through this closed Gaussian surface, and that is the spherical surface here. To do that, we know that phi e is equal to closed surface integral E vector dot ds vector throughout this spherical surface here. Now, I'll take a very small area element here, and that area element will have an area vector ds vector that is radially outwards, and the electric field intensity vector at that particular point for that area element would also be radially outward. That is given in the question. At all points in the region, the electric field is radially outwards. So we have E and ds coinciding, and that is true for all the points on the surface. Anywhere on this spherical surface, E and ds will always be making an angle 0 degrees between them. And in that case, I can say that this here would become closed surface integral E ds, because you know that E ds cos theta, which is actually E dot ds, E vector dot ds vector, will be simply E ds, where theta is equal to 0 degrees. And that is true for all points on the surface of this sphere. Now, everywhere on the surface of the sphere, the magnitude of electric field is same, because magnitude of electric field here is decided by r, and r is same for all the points on the sphere, because r is the distance from the origin, and the sphere has all the points equidistant from the origin. So we have E constant throughout. If that is true, this expression can be written as E taken out, because it's a constant, closed surface integral ds. Now, closed surface integral ds for the spherical surface will be its surface area, which is 4 pi r square. So we have phi e finally equal to E multiplied with 4 pi r square. And the question tells us that E has a value that is AR. Now, that makes it phi E is equal to AR into 4 pi r square, that is A into 4 pi r cube, because E is AR. Now, we know that Q enclosed is phi E into epsilon naught. We already know what phi E is, so we can say that Q enclosed is equal to phi E, which is A into 4 pi r cube, that multiplied with epsilon naught, that is from this equation here. And the correct answer would then be, we need to find Q enclosed. So the correct answer in the options here is option B, 4 pi epsilon naught AR cube. That is how we solve it.